Science.
You're doing extra science today, so I had to put on the goggles.
Extra science. Big science means big goggles. The goggles, they do nothing.
You're leaving the house this
Benjamin.
morning. You're leaving the house this morning, and your wife's about to ask you a question about something, and then she sees the goggles. Whoa. Leave him be. He's doing science today.
Today we are doing science. Today we are not only doing science, but we are doing interstellar science. I love it.
That's the science that happens between the science.
So wait, what would intergalactic science be?
Oh my god, intergalactic science. I actually have a question.
Oh, hold on. Let's do the
Before we
intro
get started. Yes.
Before we get started, yes. Welcome, guys, gals, and non-binary pals, to today's episode of Science Actually Presents the Nerd and the Scientist, presented to you, as always, by me, Kovi Rose, and by everybody's favorite nerd, Benjamin Salas.
Who's just wearing regular glasses. See, I'm wearing the just talk about science glasses, but you're wearing the getting knee deep and doing the science class.
Oh yeah. We are hip deep in the science.
Yeah.
So you have questions, right? What are these questions?
Hey, everybody. Today's topic is we're talking about the interstellar medium. And Kovi mentioned just now the intergalactic medium, which is actually one of the questions I had prepared for Kovi about the interstellar medium. Yeah.
I'm gonna mess up these questions so bad because I've been at a conference all week. I've not had a lot of time to do prep, and this is mostly going to be material that I covered in coursework I did in my undergraduate degree, or maybe at the start of grad school. So
Let's start it off slow.
Yeah, let's ease into it before you try to stump
Just like in a college course, the first couple days is just softball stuff, and then
I love softball.
Yeah. Anyway, no,
Yes.
I do like softball and baseball because I'm an American. But Australia has quite the formidable Australian baseball team, so you should like.
Really?
Yes.
First time I'm hearing.
Really? Oh my god! Every year there's a World Baseball Classic, and Australia is like a competitor in their green and yellow uniforms. It's quite nice.
All right. So this was an early, easy question that I've already failed.
Anyway,
Does Australia have a baseball team? And I said, maybe?
And the answer is yes.
All right, what you got?
Now, what does the Australian baseball team have to do with this topic? It's an example of what is not in the interstellar medium.
Ah, I like it. I see what you did there. Yeah.
Kovi, tell us, what exactly is the interstellar medium?
So the interstellar medium, if you break down that acronym ISM, inter means between, stellar means stars, medium means stuff. So basically, the interstellar medium is the stuff between the stars.
Right. And that is only within the galaxy. That leads to the question that we kind of accidentally stumbled upon earlier. Was, I know there is, but what is the intergalactic medium?
Yeah, there's a whole area of science, of astrophysics that's kind of... It's interesting because some people will draw... I know that some people will also disagree with this particular definition of mine, but there are those who would draw the distinction between astrophysics and cosmology to be like the scales that you're dealing with, and astrophysics is kind of the scales where you can still identify individual objects, and cosmology being like, huge scales upon which the universe appears almost, uniform and the same in every direction. And so IGM, intergalactic material, or medium, I should say. So the IGM, the stuff between the galaxies, is kind of on this borderline between what some people would call astrophysics and other people would call cosmology. But like, it's stuff, and it's doing things, and it's not completely empty, and it's not just like this cold, dead nothingness. Like, there is a flow of intergalactic materials that flows onto galaxies and is gravitationally pulled into it, and there's also material from the galaxies that pushes out against those boundaries. But yeah, the IGM, that's where it gets crazy.
Love it. But that was a question I was waiting for at the end of the episode. We kind of stumbled into it.
Oops.
Oopsie daisies. We're going to stick with interstellar medium, which is
cool.
The stuff that is in between the star systems inside the galaxy.
Mm-hmm.
Question for you about that.
Yes.
I knew that the interstellar medium was basically the bits of fluff and stuff between the stars. But when I was doing all my reading and prepping for today's episode, I was reading about all the different types of material that comprise the interstellar medium and its various densities and what those atoms are, hydrogen and helium mostly. But in all the reading I've done, all the examples for what the composition was and the density and everything, it always referenced in the Milky Way we have mostly hydrogen atoms or hydrogen molecules in the interstellar medium. The density is such and such in the interstellar medium in the Milky Way. Do we know what the interstellar medium is in other galaxies? Do some galaxies have a denser interstellar medium than we have? Or do some have a less dense interstellar medium than we have? Or have people like you with special super science classes, have you guys kind of discovered a kind of maybe constant interstellar medium amongst the galaxies?
So at the risk of answering a question that's kind of out of my depth, I don't know if there's a particular constant. I love it. You're already trying to stump me. It's 8:15 in the morning in Australia when we're recording right now. The coffee's just kicking it. So I don't know about any constant. I think that one of the difficulties in understanding the interstellar medium in other galaxies is it's kind of like a lot of astrophysics. We understand what's happening in our own backyard a lot better than we do elsewhere in the universe. And so, we've done measurements with a whole range of different telescopes, and we can figure out in other galaxies outside of the Milky Way where there are denser regions, what the composition or if we're seeing overall light that appears to have traveled through a particular composition of stuff. The chemistry in the universe is the same. It's not like there are new rules of chemistry, but I guess it's a bit harder for us to see distant galaxies with the same resolution, if that makes sense. So I think that answers your question.
It does. They're just too far away. And since we do know what the density of our interstellar medium is, do you know what that density is?
Yeah, that's something I do remember from undergrad, and it shocked me. The idea that it's basically 1 particle per cubic centimeter. So if you have an area of space that's the side of a die, like a dice, but singular, that cube that sugar cube size of space, that volume in space in the ISM, will have one particle in it, not one molecule, just one individual. Could be like one atom.
Mhm.
And that to me has just always been mind blowing. So it's both like, oh wait, space isn't empty, but it's pretty sparse.
For comparison, one particle, one atom per cubic centimeter in interstellar space compared to the air that we breathe. And the air that we breathe has 27 quintillion particles per cubic centimeter. So if you could just, do that for perspective, take a little gulp of air. I actually read, and you can tell me if I read it correctly, but the one particle per cubic centimeter density of interstellar medium is not constant throughout. There are some pockets where it's more dense, some pocket where it's less dense, and it ranges actually from about 100 particles per cubic meter to about 1 trillion particles per cubic meter. That's where the interstellar medium ranges, which 1 trillion atoms per cubic meter sounds like a lot, but really it's, if you just quickly go back to the math that we just mentioned, about one particle per cubic centimeter in space and 27 quintillion per cubic centimeter in the air you breathe, you'll see that 1 trillion is actually nothing.
Yeah, it's
considered
not much.
Some of the denser parts.
Yeah, that's a really good point. The one particle per cubic centimeter is on average, and there's so much stuff happening in space, and even in that interstellar medium between star systems, between solar systems, you can have, if we look at the area around our sun, so our solar system is in a region of space that's often called like a void, because as best we understand, a long time ago, but not in a galaxy far away, right here, there were a couple of supernova, at least I think 2 or 3 supernovae that went off around similar times, and the shock waves from those supernovae kind of all pushed stuff outwards, and our solar system is in that kind of lower density area, where all the stuff just beyond like the border of the shock waves from these supernova has created. Outside of that, there's more stuff there, but inside where our solar system is, it's a bit less dense. And then by comparison, you have interstellar space in, like a nebula, where technically is interstellar medium, but it's actually just one giant cloud of dense gas that's forming new stars. I mean, there it would be incredibly dense. So yeah, it's all relative.
So is a nebula part of the interstellar medium, or is a nebula an object that's in the interstellar medium like our star system is? Because a nebula is kind of, well, given its name, a nebulous form, so it doesn't really have a sharp edge to it. I guess neither does our solar system, but we have like the heliopause. That's the end of our solar system. I don't know that a nebula has a specific end to it, but
that's a good question. I mean, at the end of the day, we try to kind of impose human conditions, human boundary conditions on the universe, and be like, okay, this is where the solar system ends. The solar system ends at Pluto. No, wait. The solar system ends at the Kuiper belt. No, wait. The solar system ends at the heliopause. And then people are like, no, well, the solar system ends at the point at which the sun doesn't have a gravitational influence. But, like, technically that sort of goes on, infinitely and just gets infinitely smaller and smaller. I think I think with nebulae, it's really cool because those boundaries, as you said, are less well defined. And so if we look at something like a planetary nebula, which I don't know if you want to get into this now or if you want to do this after the break, but a planetary nebula has normally a single star in the middle, and then at a great distance out of it, you see this kind of shell of stuff. But that shell of stuff is interacting with the ISM, with the interstellar medium. And like with that, where would you draw the boundary?
Right.
You know? So,
Cool.
yeah. We can talk more about, I love planetary nebulae. I love the history of planetary nebulae as well. So we can chat about that now, or we can wait until after the break if you'd like.
Okay. All right. Leading us into the break, though, only one man-made object has reached the interstellar medium. Do you know what it is and when it happened?
The object that was this. Did this happen to be something that we spoke about recently?
We did.
Did this happen to be something that holds a particular record?
It holds several records, one of them physical.
Let's stop teasing our audience. What is that?
Voyager 1 is the first artificial object, man-made object, to actually leave the solar system and reach the interstellar medium. And it did so by crossing the heliopause on August 25th, 2012. So any of our listeners who had a birthday on August 25th, you got a special little trivia tidbit there about your birthday.
There you go.
Way to go,
very nice. Nice. Very nice. Hey, Benjamin.
Yes, sir.
Are you bored of empty space?
Like you have no idea.
Well, then I've got something for you. Discover the interstellar medium. It's a cosmic mix of gas, dust, and mystery. Need a pit stop? Try a nebula for those perfect space selfies. And cosmic rays? Great for this out-of-that-world tan. Just pack your SPF 5000. The interstellar medium, because even the void needs variety. Warning, travel at your own risk. SPF 5000 not included.
I like it. I like it. Hey, Kovi.
Hey, Benjamin.
Are you tired of the same old morning routine? Are you looking for a cosmic kick to start your day?
Oh, yeah.
Well, let me introduce you to, my friend, the Interstellar Medium additive for your morning coffee. Infused with the essence of the universe, each sip takes you on a journey beyond the stars. Elevate your mornings with flavors that are out of this world and out of the solar system. Whether you're navigating the corporate galaxy or exploring new frontiers, our Interstellar Medium additive will add fuel for your adventures. Blast off into a stellar day with the Interstellar Medium additive, available at select stores and online. Taste the universe.
We'll add fuel to your fuel. Oh, that's great. So good.
Seriously, though, people who want to sponsor the show, we're ready.
Oh, yeah.
Anytime,
we've had lots of
whatever.
Oh, God. That's great. That's great.
Good stuff.
Yeah. So planetary nebulae, right? Have nothing to do with planets.
But that's where planets come from.
Planetary nebulae have as much to do with planets as the Horsehead Nebula has to do with horses.
No.
Or as the Milky Way has to do with milk.
Well, the Horsehead Nebula has a name because it looks horse-ish, and the Milky Way has its name because it looks milk-ish. But the planetary nebula is a thing from which planets come from. No? Well, What's the difference then between an accretion disk around a star and a planetary nebula?
So there are a few things to unpack. The first thing is that you were so close to stumbling into exactly why planetary nebulae are called planetary nebulae,
Okay.
which is because astronomers like William Herschel in the late 1700s thought they looked like planets. But essentially, planetary nebulae are stars that have shed off their external layers. Those layers have created a bubble around them or all sorts of weird shapes. And those shapes, when seen from Earth, sometimes they'll look like a ring, sometimes they'll look like a little Eskimo, sometimes they'll look like dumbbells, but generally it's just a shell of stuff, or sometimes it can be a double-lobed shell of stuff that will have all sorts of shapes when we see it. So planetary nebulae are nebulae that happen to look like planets. But to the second part of your question, so an accretion disk generally is just like a disk, a ring of material that's like falling onto another object, but it kind of forms, a disk of stuff as it falls onto it. Generally, we'll speak about an accretion disk around a black hole, or in some cases, around degenerate stars. But I think what you were talking about was a protoplanetary disk.
Yes.
So
an accretion disk can become a protoplanetary disk if the conditions are.
Again, it's one of these things where humans just like make up names for things, but like, yeah, what it describes is basically like you were spot on. It's stuff that's orbiting around a star that's left over from the formation of the star, and that disk of material will be the disk of material from whence planets form. And that's why you'll notice that in most star systems, like in our solar system, the direction in which the star is rotating will also happen to be the direction that the planets mostly are orbiting, because the conservation of angular momentum from the stuff that falls in, that stuff falls in with a particular rotational velocity. It's moving around in a certain direction, and that causes the star to form rotating in a certain direction. And the planets that form from that protoplanetary disk will also rotate in that direction.
Love that. Nice.
Ka-chow.
Ka-chow.
Yes, but enough about me. Let's talk about ISM. More questions.
I love it. Do you know when the ISM was discovered?
It was a Tuesday.
Yes, actually. Kidding, no.
Prove me wrong, I dare you.
It was. There were a couple discoveries that led up to it. William Huggins, in 1864, used spectroscopy to determine that a nebula is made of gas.
Mm-hmm.
In 1889, Edward Barnard, using deep photography of the sky, found a lot of holes in the Milky Way. We first thought they were similar to sunspots on the sun, but they are now known as dark nebulae, dusty molecular clouds on the background of the star field of the galaxy. Mm-hmm. And it was in 1904, using those two discoveries, that Johannes Hartmann made the first direct detection of cold, diffuse matter in interstellar space by observing, on a Tuesday, the binary star Mintaka with the Potsdam Great Refractor. He discovered an absorption from the K line of calcium. And that's the first detection of interstellar stuff.
I love it.
So,
I love spectroscopy. It gets me so excited because it's so wild that we can figure out the chemical composition of clouds of stuff that are hundreds of billions of kilometers or miles away from us, purely based on very subtle changes in the rainbow of light that we're getting from those things. That's mind-blowing.
absolutely. In 1909, Festo Melvin Slipher confirmed that the interstellar medium was mostly in a gaseous form. And then he also discovered in 1912, a few years later, that there is also interstellar dust.
Ah, yes.
Can you tell me, please, because I actually don't know, what's the difference? And in what way is what's the difference between interstellar gas and interstellar dust if everything is at an atomic level, like as we discussed earlier, about 1 particle per cubic centimeter? An atom is an atom and an atom.
An atom is an atom and it's an atom. Yeah. I mean, astronomers tend to consider most things that aren't hydrogen or helium to be metals. Anything that's not hydrogen or helium is metal. And so when you have metals that are forming molecules, they're no longer... So you can have, hydrogen gas, atomic hydrogen gas, and you can have molecular hydrogen gas when there are hydrogen atoms that are bonded together in molecules. And so, from my understanding, the metals in molecules that start building up to larger forms and clumping together, that is kind of the basic definition of dust. From memory, again, I don't work on dust. There are a lot of people much smarter than I am in my department who do work on dust, which is especially... it's something that you can see really well with infrared telescopes, because especially when there's a star nearby that illuminates that dust, the dust's temperature changes, which means that the thermal radiation that you see from it, especially with infrared telescopes, will get brighter. You can also end up with more dusty material as a result of stuff that's left over from the formation of other objects. So you can have stuff that clumps together following the formation of stars, like I was talking about earlier with protoplanetary disks. So all of that stuff, that heavier, rockier material, that's dust. Yeah, gas is going to be, generally speaking, atoms in a simpler form.
Awesome.
Yeah.
Hey, Kovi.
And I hope there are no spectroscopists listening to that who are like, no, it's all wrong. I hate it.
Oh my God, I hope they are listening and they are thinking it's all wrong, and then they want to come on the show and tell us about it. What's the three-phase model?
The three-phase model. Oh God. I know this.
I'll give you a hint. There's 3 phases in the model. See?
These are the temperatures, right?
Yes.
Yeah. I'm going to embarrass myself. I know that you've prepped much better than I have for this. I'm trying to recall from memory from a decade ago. But yeah, tell us what the 3-phase model is.
The cold, dense phase, consisting of clouds of neutral molecular hydrogen. And then there's the warm intercloud phase, which consists of rarefied neutral and ionized gas. And then there's the very hot phase, gas that's been shock heated by supernovae and constituted most of the volume of the ISM. And I did not know. Are we talking about three different ranges of very cold temperatures because calling a part of the interstellar medium very hot, where I assume there's not a lot of heat. I think we're talking about very cold temperatures.
Not always. There
Really?
are, yeah, you can have emission nebula that get pretty darn hot. Like you'd be surprised because when you're talking about, like you said, so you mentioned shock heating and you mentioned ionized gases, right?
Mm-hmm.
So when you're talking about an ionized gas, you can end up with temperatures that are in the range of like thousands of degrees. Space can be surprisingly hot sometimes.
Yeah, apparently. I did not know that. I just thought calling something very hot is just when we had our guest on Earth before, last season, about dark matter and dark energy. There were temperatures, but they were all very cold temperatures. And so I was just assuming, well, yeah, same that quirky astrophysics method of naming things cold and warm and hot, even though that's relative to themselves, not to anything like a boiling pot of water. But I guess so.
Right.
See, we're learning. We're learning. I have another question.
Sure.
There's so little stuff in the interstellar medium. I mean, there's a lot of stuff, but it's very
so
sparse. And it makes up 15% of our galaxy, which I find out very fascinating. As empty as the space is between the stars, 15% of the mass of 15% of the particles of our galaxy are in the interstellar medium. Stuff so small, so far apart. How can we observe it? What methods do we use to actually observe very little at all?
How do we observe nothing? Yes.
I didn't say nothing. There's something.
Yeah. So we've spoken briefly about spectroscopy, and I think that we're going to go back to it again. So when you have when you have electrons in an atom, right? So in this like simplistic model of an atom, you will have the nucleus of the atom, and then you have different electrons that are orbiting around it at different distances from the nucleus, different energy levels, right? When you shine light, or when that atom is irradiated with light, with photons that have particular energy levels, you can release one of those electrons from it, and the light in turn is absorbed. So basically the light is eaten up by the electron, but it transfers its energy to it. So the light is absorbed. And that will happen at a particular energy level, which corresponds to a particular wavelength of light. And the inverse process can also happen when an electron releases a photon as it drops down an energy level. And so it will do that in a discrete, quantized level of energy, which corresponds to a particular photon energy level and wavelength. And it emits that photon. And so when this happens, this process of absorbing or emitting photons, depending on the atomic energy levels, we can tell you exactly what the composition is of that stuff that was doing the emitting or absorbing, right? That's like the fundamentals of spectroscopy, of emission lines and absorption lines. And so if we're looking at an area of space that looks mostly empty, but there is a star behind it, and we know what sort of star it is, so we know what the chemical composition of that star should be, but we see additional emission lines or additional absorption lines in the light that's coming from it, we can figure out what the composition is that way. That would be kind of the main way. Again, this is not the sort of astronomy that I work on personally for the most part, but that would be one of the main ways we could figure out what this stuff is.
That's awesome.
Also, when you look at like different wavelengths, you will see a completely different picture. So if you look towards a particular region with the naked eyes with visible light, you might not see much. If you look towards a region with a radio telescope, the whole area that you're looking at that seemed to have been filled with nothingness might suddenly be bright in the radio because you're observing at, for example, 1.4 gigahertz, and that is a wavelength that corresponds to an emission from hydrogen gas. And so you're seeing that hydrogen gas illuminating that region of sky, even though you wouldn't have necessarily seen it at other wavelengths.
Oh, well, that's cool.
Yeah.
I love that. So I know what the
Space
star
is
is,
cool.
and that star becomes background, and then you can just see whatever else is that shouldn't be in the star is there.
Yeah.
Nice. All these little tricks astronomers use. This is fantastic.
We're very sneaky that way.
It is sneaky, but I think it's kind of cool. Someone had to think it up. I'm staring at the star that's making only these things, and today it has blood in it.
It's full of blah.
Because some blood passed in front of it between itself and me.
Yeah, it's pretty wild.
Fascinating.
Fascinating. Yes. Yes.
Are there any other ways to observe the ISM?
Other ways to observe the ISM. I mean, I'm sure there are others that I don't know about. Again, I don't work specifically on ISM physics. I know that, I mean, one of the things that I work on also with radio telescopes is supernova interactions with material. I could mention that briefly if you'd like, if you're interested. So, there's actually a paper that we've submitted recently on this topic. But basically, when massive stars, so like you're talking, let's say upwards of 8, and maybe let's say 8 to 30 times the mass of the sun. So these stars are losing material over their lifetime before they run out of nuclear fuel to burn, and then basically there's nothing holding up against the gravitational infall. So gravity causes the star to collapse. There's a whole bunch of really cool neutrino physics and stuff happening that causes a shock wave to be launched to kind of explode in a supernova. And as that supernova starts moving outwards, it interacts with all the material that the star lost, that the star was throwing off in these tantrums as it lost material in the years prior to explosion. And so radio astronomy is a really good way of doing like a CSI type investigation. Well, it's circumstellar material, it's circumstellar medium, and you can figure out what amounts of stuff was lost and pushed out into the CSM and the ISM before the supernova exploded, before it went off. And you can do that just from monitoring the radio light from the star.
That's cool.
Yeah. And it's pretty wild that you'll see it sometimes years after the supernova. Like, supernova, we discover it with an optical telescope, and it goes, boom. And then 10 days later or 20 days later, it's, faded out. And then a few months, or in some cases a few years later, looking at that same point with a radio telescope, suddenly it's just like get illuminated as the shock wave hitting the surrounding material produces that radio light. Yeah. Okay. It's wild stuff.
I've been seeing a lot of headlines popping up that yet again it's getting trendy, I guess, in the news that Beetlejuice is going to bugger off soon. it's, I've seen it ranging in the headlines over the years, from in our lifetime to it's imminent to, in a couple of decades.
I think
It's just what makes the headlines change. There's like a certain little shutter or some sort of little flicker that we can't see, but radio astronomers can see, that there's some sort of, I don't know, uneasiness happening over there.
So there have been people who follow the variability of stars, especially with optical telescopes, a lot more closely. And when a star is either normally more constant and suddenly varies, or normally varies in one way but suddenly starts varying in a way that's more random, more stochastic, like there's been signs of this happening with Betelgeuse, people kind of lose their minds and like, oh, this massive star is finally about to kick the bucket. But I think that we should, I can agree with the fact that it will explode soon, but soon on astronomical timescales is very different to, it's like that old joke of the guy who's like, talking to God, and he's like, God, what's a minute to you? What's a million years to you? And God says, oh, it's like a minute. And the man says, okay, so what's $1 million to you? And God said, oh, it's like $1. And so the man says, hey, God, can I have $1? And God says, sure, in a minute.
I love that joke.
So I don't know why that's still in my brain from my childhood, somewhere in the dark recesses. But the point stands.
It's a beautiful joke.
The point stands that the universe does not work on timescales that particularly care about news cycles or human lifespans.
Right. That was great.
That's good. Is that a good note to end on?
That is a good. Not only is it a good note to end this episode on, but I think ending our 30th episode, wrapping up our third season on such a good job.
Damn.
That was perfect. 30 episodes. See? It happened in just a minute.
Just a minute.
Just took a minute.
I love that. Yeah, wow. 3 seasons. I can't believe it's been 3 seasons.
It's been great. I want to do another one.
What's that?
I want to do another season.
Oh, we've got to do at least one more season.
At least one more, give or take, many.
Give or take many.
Many.
Well, I think we'll do as many seasons as the people want.
Or until Betelgeuse explodes. As many as we can.
Or until,
because it's going to happen soon.
Oh man. Yeah, I'm just like looking at the at our analytics, and like to the nearly 2,000 people who've downloaded our episodes.
Yeah, it's like 1880 something.
Huge thank you. Yeah, I'm constantly, every time I open up the analytics page, which is so easy to access, and there's so much information there, and it's so simple to get great analytics for to learn more about our wonderful listeners. I'm just overwhelmed and really humbled by knowing that there are folks all the way from Australia to Ecuador to
thank you to that
Uganda.
one guy in Uganda. Yes.
Yeah.
Yeah.
Yeah, right by Lake Victoria, just north of Lake Victoria. I hope you're
going
out on that lake.
Thank you.
Yeah, thank you so much. Thank you to all of our listeners. This is really lots of fun. I mean, for both of us.
Oh, absolutely.
This is great.
This is one of the highlights of my week, if not the highlight of my week. It's fantastic. It's fun.
Yes.
Talking science.
It's fun. I want to keep doing it. Benjamin clearly wants to
Done.
keep doing it.
We shall keep it going.
We'll keep it going. It is decided.
Done. There you go.
But
this is us having a
please,
meeting. You guys were all the witnesses.
yes, the motion has passed. To all of our listeners, thank you again for listening. And if you want to keep listening, and if you would like to tell us what sort of topics we should speak about in the next season, in season 4, what sort of guests we should have in season 4, if you want to recommend folks to us, drop us a message, email us, tweet us, linked us, drop us a message on ye old Facebookie. Find us on all the socials and let us know how you feel. Benjamin, where can the people find you?
I think Kovi already named all the places. Go to those places: Facebook, Twitter, Instagram, TikTok. What else? Threads, Blue Sky Hive, Mastodon, and just look for Science Actually on all those things, and you'll find me. Kovi, where will they find you?
If folks look on all of those wonderful social media platforms that are obviously only having a positive effect on our society and nothing else. Nothing else. If you look for Fun Fact Science, you will find me at Fun Fact Science. You can also look for the Nerd and the Scientist podcast page, and you'll find us. You can find our YouTube. You can find us on TikTok. Have a listen. Have a watch. Drop us a comment on the YouTube page of any video that you particularly loved or particularly hated, and it will teach us and we will learn.
I am happy for any feedback, exactly for that reason. We'll learn, and we will grow, and we become better, and we're going to season 4 the hell out of this show next season.
Heck yeah. Heck to the yeah.
Heck to the yeah.
Heck to the yeah. Thank you guys